Hi, I'm Dana Rayan. I spent the last 2 days studying backpropagation of neural networks. I'm a Cal State LA computer science student in CS 4540, which focuses on artificial intelligence. Three Blue, One Brown's video about backpropagation is what we're going to use as the focus here. So his video discusses his creation of a neural network which reads handwritten digits, which are kind of like pixelated little numbers. A bunch of people write down numbers, and we're testing to see if that neural network knows how to read these numbers. Now, 3B, 1B takes viewers on an intuitive walk through backpropagation and its algorithm. So backpropagation is the core algorithm of how neural networks learn stuff from us humans. We're also going to be looking at the use of derivatives and the rate of change of graphs and how we use that to compute something for the network. The network has 2 hidden layers and a 10 neuron output layer. The corresponding output layer tells us the network's answer to the written number. So taking a look at a view of the hidden layer and the output layer. Here is a visual of these two. Now our output layer right here, this is going to give us the answer of the machine. So let's say we put in a 3. We don't really know what it's going to give us the answer to. Hopefully it's also 3, but if it is, it'll be solid right here at the 3. So the output layer kind of tells us the final answer of the network. So I just went through that. The total cost of the network lets us know how accurate our neural network is. So weights and biases are tools that help us minimize this cost. And granted, we always want to minimize cost in life in general, so looking at it in that parallel kind of helps. We're going to be looking at the gradient descent of something, and we want to find the local minimum of a graph in order to really find that minimum point of how do we spend as little as we possibly can in order to get the most accurate answer that we can. So to calculate this cost, we take a look at what the machine actually gives us as the answer, subtract that from what we want the answer to be, and square that difference. And then we add those all up. Once we add those all up, that gives us the cost of a single digit. So let's say all the answers for 2, all the answers for 3, and so on. The average of all these results gives us the total cost of the entire network. So we take those individuals for 1, 2, 3, 4, 5, 6, etc. We average those all up, and that gives us the average for the entire network. And here's a visual for the total cost. So in order to minimize this cost, like we said, spending money is optimal. Weights and biases will help us figure out how can we manipulate this cost function to give us what we need in the most effective manner. Again, derivatives are going to help us. And apparently seeing derivatives in calculus class and seeing derivatives in backpropagation kind of feel a little different. But the gradient answer to the question, which weights and which biases minimize the cost? This also kind of gives us the minimum location of that graph. So our negative gradient is going to give us something that helps us find that. So the gradient is a vector, and each one of these components, C1, C2, C3, all the way up to however many components there are going to tell us what we need to do to change the cost, if we do need to change it. So how can we change things up for the cost to decrease? We're going to use math to manipulate it. So here we have the negative gradient vector with all the weights and biases inside of the vector. And here we have our cost function. The cost function kind of resembles every single little cross section of the neural network. So components of the cost function, obviously, like vectors do have, they have magnitudes. So taking these magnitudes into perspective in their directions, it kind of tells us what we need to do with the cost function in order to really maximize what we need out of it. And we'll go into detail right now about that. So these components, as weights and biases, tell us how we need to change things in order for the cost to decrease. For example, if we have a component inside of the negative gradient vector that is a 3.2, multiplying it by something is obviously going to increase that thing we're multiplying it by more than 0.1 on the right hand side in pink. But that doesn't tell us enough. What we really need to know is which changes are going to save us the most money. So through Hebbian theory, we know that neurons that fire together wire together as well. So how does that connect to backpropagation? Well, if they wire and they fire together, the likelihood of them aligning the most means that these are the neurons that are the most active. These also give us the most accurate answer. So increasing accuracy using math, which we'll dive more into in the next couple of slides, will help us make more sense of the mathy point of view, but from a statistical point of view, I believe that's what I'm understanding from Hebbian. So propagating backwards applied to a single training example, nudging its weights and its biases up, down, and through relative proportions, applied right before the final layer of the neural network is reached, will get us that optimal output. So the math of the neural networks that we're looking at, so 3B, 1B kind of throws out this formula. So what are we going to do with it? So this 0.2 here on the left side of the equal sign, how can we increase this value so that way activation of the neuron increases, and that way the firing is more likely to align with where we need it to? Well, we're going to use the right hand side of the equal sign. So specifically, let's take a look at the bias. So we need to increase the bias. That is the most simple part of manipulation here. Another thing we can consider is increasing the weight, which are the W variables here. So in order to effectively increase that 0.2 on the left side of the equal sign, the A as well has to proportionally increase in order for the math to do what it needs to do. So the activations of A sub I help the weight proportionally. So we have to increase every single parameter of the vector space that we have here in order for it to really increase 0.2, because if this wasn't proportionally increased to W on this side, then we're not going to get what we need out of it to get the most out of the cost function. Another thing we can consider is changing the activation, which is the A variable. And A comes from previous layers of the neural network. So how do we make a neuron more active? Again, we're changing previous layers. So every time we see this positive weight coming in versus a negative weight, we want that positive weight to shine through more than the negative weight, because we want the positive values to have more weight than negative values. Because if the negative values have more weight, then we're not going to have as high of an output on the other side of the equal sign. Just mathematically speaking, super logical, then 0.2 increases, and this increases the neuron's activity corresponding to weight. So propagating backwards, this helps us add that desired effect that we want. So the nudges are kind of sliding the little slider around that helps us increase what we want to increase, which are those previous slides that we just went through, discussing how mathematically multiplying a weight to an activation corresponds proportionally. And then that process recursively applies over and over to previous layers. So it goes backwards, like it says in the name. Now, unfortunately, everything we just learned about doesn't really apply to the real world, because it's not realistic for a computer to keep doing the gradient process over and over and over again for so many data sets. It's just not realistic, and nor does the computer have the capability to do so in a timely manner. So we take a look at the data after shoveling it randomly and then creating mini groups of it and then working with those chunks individually. These are called mini batches. And then we step into the gradient descent. So this eventually converges into what we call the local minimum of the cost function. And this helps us achieve our main goal, really, which is reducing how much cost or spending money we're doing when the neural network runs through all the data. This backpropagation algorithm little photo was interesting to me. Initially I noticed how the error decreased here at the bottom. And now the goal states that we want to get the error of g prime of x to approach 0. And this creates a smaller numerator of e2 squared versus the numerator here. And the reason why this numerator kind of decreases is because the weight is what's changing, which is what we discussed earlier. So the weight changing its value gives us a lower derivative. So we're experiencing less change. And that's kind of the big idea, I believe, behind backpropagation. Decreasing the weight leads to less of a derivative spike. So yeah, I thought this was helpful. And thank you for watching my video. Like and comment, subscribe below.